It did. All right. Okay, so last time we looked at the origin of the mole. We saw where it comes from, why is it called a mole, why we should use it. We looked at a couple of calculations about the mole. And we ended when we were calculating, after calculating reaction, different things using reactions. So we calculated like volume, calculated moles, molarity, and things like that. I would encourage you to go through those notes again, which I sent out in the group. And if you don't have them, you can always ask, and I'll always send them. Okay. So today we'll start with solutions. What you do with solution as you measure them. So this is sort of volumetric analysis, and it's still part of mole concept. Okay, which is very, very key in both theory and practical. Huge for those two things. Very, very huge, very key. So now let's start with solutions. And please ensure to ask questions where you don't understand. Okay, let's start with dissolving a solute in a solvent, which makes a solution. Volumetric solutions are made by dissolving a known amount of solute. Remember that, a known amount of solute in a solvent. Usually the solvent is water, and then adding enough solvent to get the correct volume of solution. So again, you have a known volume of a solute, you dissolve it in a solvent. After dissolving in a solvent, then you add more of the solvent to reach a certain volume that you're looking for. Okay, that is the way to make a solution in volumetric analysis. Now, here is a perfect wrong way to do it. If you ever want to do it in a wrong way, this is how you should do it. So if you want to do it in a wrong way, just get, like for example, you dissolve 1 gram of a solute in 250 cubic centimeters of deionized water. Someone just joined with audio. If you join, please turn off your audio, okay? So that you don't interfere with people who are already concentrating. All right, I was saying if you want to do it the wrong way, this is how you do it, okay? First, if you could give me the permissions to mute, that would be great, so that I can do that easily. Okay, as the host works on that, let us continue. I was saying the wrong way to do this, to dissolve any solute into a solvent, would be this. So you get your known amount of solute, which is like 1 gram, and you immediately dissolve it in 250 cubic centimeters to make a solution. That is the wrong way to do it, okay? And we shall see why. Now, you'd ask, what is the right way? Here is the right way, and it will give you the reason for not doing it the wrong way. The right way is you get, I don't know if the host can hear us, but I would suggest you give me the permission to mute so that it is easier for me to do that. Okay, good job. I've seen it now.
28.
Okay, I've muted her. All right. Now that everyone is muted, we can continue. Okay, I was saying, we have seen the wrong way. Let's do it the right way. So the right way to make these solutions is you dissolve, well, for example, you have 1 gram of solute, you dissolve 1 gram of solute in water, okay? just a certain amount of water. Make sure it is dissolved. Then add enough water to make up to 250 cubic centimeters of solution. So you start with the solute, okay? Then add water to dissolve it as you stir. Once it is dissolved, that's when you fill up to the certain volume you wanted, which is normally in the laboratory we use 250 cubic centimeters cubed, okay? That's what we use normally. So this is the right way to do it. Start with the solute, dissolve it in water. Once it is dissolved, then add to the brim of the volume that you want. That's the right way to dissolve a solute into a solvent. This eliminates any errors in terms of solubility of that salt in the solvent. It is important for you to remember this step to be key in your practicals. In O level, it was different that your teachers used to mix for you these things. In A level, it's a little bit different. Some of them you have to mix by your own, okay? By yourself. So they'll give you the measurements they want you to mix, and you'll have to do that on your own. So they say like dissolve this amount in a solvent, then do the following practicals. And if you do it the wrong way, you're going to get wrong results. But if you do it the right way, your results will be more close or accurate compared to the examiner's answers that they need. Okay, so it is key for you to remember this. Huge for volumetric analysis. All right. Let's look at this example. One whose concentration is known accurately. Okay, a standard solution. In case you ever asked, what is a standard solution? A standard solution is a solution whose concentration is known accurately, very, very accurately. That's a standard solution. Example we have here, 4.24 grams of sodium carbonate was placed in a clean beaker and dissolved in deionized water. The solution was transferred quantitatively into a 250 cubic centimeter graduated flask and made up to the mark with deionized or distilled water. Okay, now here you are mixing a solution. The first question you can be asked is, what is the concentration of solution in moles per decimeters cubed? Okay, so we have our question here. What would be the first thing that you do in case you ask this question? What is the first thing you do? We are finding the concentration of solution in grams, in moles per decimeters cubed. In other words, you're finding the molarity of this solution. We have dissolved these grams of sodium carbonate into this volume. Okay. What do you do first? We have seen this many times. Last time we saw this type of questions very, very many times. So you should be able to remember this. Who would love to try to tell us what we do first here? Yes, Bonita.
We first find the molar mass of sodium carbonate.
Okay, the molar mass of sodium carbonate. Right? Yes, and here we have just listed what we have. And yes, the molar mass is the first thing that we found as we listed what we had, which is right here. The molar mass now it should be very, very, very easy for you guys to find. Last time we did so many examples. But for those who are absent, the molar mass, you just get the individual relative atomic masses of each atom, add them up. Okay, for example, the relative atomic mass of sodium is 23. 23 times 2 because we have 2 atoms, and then plus 12 carbon, and then plus 16 times 3 of oxygen. The total it gives you is 106 grams per mole. That will be our molar mass. So far, that means we have the mass of sodium carbonate in 250 cubic centimeters, We have the mass of sodium carbonate, and then we can find the number of moles. Okay, very easily. The number of moles. Someone has a question. Let's see. This is Ivan. Yes, Ivan. Ivan, you have a question?
Yeah, my friend corrected me.
Your friend corrected you?
Yeah.
Well, that was quick. Good job, the friend. I don't know which friend is that, but good job, whoever it is. Okay, Ivan was corrected. So when you have the molar mass and you have the mass, you can easily find the number of moles. You remember our triangle? If you remember our triangle, then you know where we have got the number of moles. Okay, number of moles is always equal to, who knows the formula? You can remind us of the formula for finding the number of moles according to the triangle we looked at last time. We made a triangle to keep reminding us. Every time you're calculating molarity, just draw that triangle. What you're finding, you cover it. It gives you the formula. Yes, Sharon? Sharon?
Mass divided by the molar mass of the substance.
Exactly, mass. Yes, mass divided by molar mass of that substance will always give you the number of moles. Okay, so the number of moles of sodium carbonate in 250 cubic centimeters will be equal to this, which is 0.0. Now, we have the moles, we have the volume. We are finding the molarity, right? What do we do? Next step now. Who can suggest for us the next step? Yes, Tiaba, you are correct. Given mass over molar mass. We have here our volume, okay, which will fill to the brim. We're finding molarity. We have already found moles in 250 cubic centimeters. Remember, molarity is contained. I won't give you that hint to make it too easy. Besides Sharon, who else would love to try? Charles. Yes, Charles? Charles, you want to try? Unmute your volume and speak. If you're speaking, just know we can't hear you. So it's probably your network. Let's go to Anthony as Charles sorts that out.
For my zinc, 0.04 moles are contained in 250. Then we are supposed to look for that one in 1,000 in order to get the molarity.
Okay, good job. Remember, molarity is what is contained in 1,000 cubic centimeters. So that's good. Is there any other suggestion? Ivan, do you have a different suggestion?
Yes.
Mm-hmm.
It is 1,000 centimeters cubed contain 0.4 moles. The ones that 0.04 moles. Then 250 will divide this number of moles by 1,000, then multiply by 250 to get the number of moles.
All right. So remember the number of moles in 250 cubic centimeters solution is right here, is what we found previously. Okay, so it's important for us to remember that. Now we are finding the molarity. Okay, what we shall do is to remember that the units are different. If someone who introduced 1,000, you'll know why now. The concentration normally is expressed in moles per decimeters cubed of solution. Therefore, as it is in 250 cubic centimeters, the value is scaled up by a factor of 4. So now here we are introducing the 1,000. It is scaled up by 4 because we want to accommodate the change in decimeters cubed. Okay. So therefore, the number of moles in 1,000, okay, will be 4 times 0.04, which gives us 0.16. This is the same as you saying, okay, 250 cubic centimeters contain this. And then what about 1,000 to contain that? To give you 4 times 0.04 as your molarity. Okay. It is in first principles. I'll try to explain it simply in first principles, where the scaling up comes in by a factor of 4 on this number of moles. Okay. This is like getting 1,000 divided by 250, okay, cubic centimeters, all right, multiplied by 0.04, meaning that we found the moles in 250 cubic centimeters to be this, all right. So you can start by saying 250 cubic centimeters contain these moles, all right. And then what about 1,000? Because molarity is contained in 1,000 cubic centimeters. Okay, what about 1,000? You'll get 1,000 multiplied by this, divide by 250 cubic centimeters. And when you divide 1,000 into 250 cubic centimeters, you get 4. This is where the 4 is coming from. You get 4 multiplied by 0.04, which gives you 0.16 mole. Okay, so that will be our answer in this case. Any questions? All right, good job, good suggestions. Let's continue with more examples. We shall get there in case you don't understand. All right, here we shall concentrate on, again, a standard solution and how to work out how much to weigh out. In case you're asked to weigh or you're asking to find mass. Okay. Someone is asking, what was the question? The question was right here, the one we started with. Okay. All right, let's continue. Another question is right here for us to figure out. It says a chemist needs up to 250 cubic centimeters standard solution of 0.1 molar of sodium carbonate from anhydrous sodium carbonate. How much will they need to weigh out? So here they're asking us to find the mass that will be contained in 250 cubic centimeters of 0.1 molar sodium carbonate. So now we are concentrating on mass. Okay. Again, what shall we do first? The answer is always constant, almost. Yes, Charles? Charles? I don't know why we can't hear you. You unmute your volume, but we can't hear you. Trevor?
Can you find the molecular mass?
Okay,
And after you multiply the number of moles times the molecular mass, I think.
Okay, that's good. All right, it's important to know the molecular mass always. Okay, you have to know it in the back of your mind. It will help you later. Let's see what we have here. So we have a concentration that we have been given in molarity, which is moles per decimeters cubed. How many moles will be in 1 decimeters cubed? The same as saying 0.1 mole, okay? But if it goes into centimeters cubed, or if you ask how many moles will be in 250 cubic centimeters, then this is where we introduce the 1,000. Therefore, we are dividing by 4. So for example, you can say in first principles, to find this, you'd have to say 1,000 cubic centimeters contain this, okay? 1,000 cubic centimeters contain 0.1. What about 250 cubic centimeters? So in that case, you'll have 250 multiplied by 0.1 divided by 1,000, which gives you a quarter, or 1 out of 4, times 0.1 times 0.1, okay, which gives you this. So in first principles, that's how you would write it, that 1,000 cubic centimeters of sodium carbonate will contain 0.1 moles. What about 250 cubic centimeters? Okay, then you cross multiply, and once you do, you get this answer. Remember, I told you need to know how to rearrange mathematical formula for you to calculate these numbers easily. It will help you not to always ask, hey, where is a quarter coming from? A quarter is coming from 250 cubic centimeters when you divide them by the 1,000, okay? Remember, the reason why we introduced this 1,000 is because we are changing from decimeters to centimeters cubed. It's important to remember that. So here you get a quarter times our moles, and you get, these are the moles in 250 cubic centimeters. So now you have the moles in 250 cubic centimeters. All right. What is going to be our next step? Hey, Melissa, have you now got the 4? Because I've explained it. Unmute and say yes or no, then I'll repeat if you have not. Melissa, have you got the 4? Where it is coming from? Let's see if you've got it. Oh yes, she has got it from the chat. Okay, good job. So this is where it is coming from, right there. Just explained it, okay? Right there. I hope everyone is getting it now. I want to go very, very, very slow so that you never have any problem with mole concept again. Okay, that's why I'm taking it slow as I can. All right, so what do we do next here? We have the moles. Remember, in your mind, you have to know we're concentrating on finding mass. So, what do we do next? What do we do next? Last time we looked at a very nice formula that can remind us of this. I don't know why I introduced formulas instead of first principles, because formulas, they are easy to remember, especially the 2 triangles we have looked at so far. Now here, the second triangle can help us very quickly. So if you had gone through those notes, you would see those triangles and they would help you. Right now, you would be not finding any problems, okay? All right, so remember the relative molecular mass, this is when it comes into play, okay? Every time I talk about triangles, just now remember molecular mass is gonna be involved. So here the molecular mass comes to play, all right? Remember, it's something you always have to first find. Okay, do not wait to find it later. It's easier for you to first find it so that in the future when you need it, you just use it immediately. So here, in this case, we're going to need it at this particular step, okay? So the molar mass will be 106 grams per mole. And if you still have problems finding the molar mass, I would suggest you look out for that video of the previous lesson. We did a great job in finding molar mass. And we even gave the difference between molar mass and relative molecular mass, and the difference between relative molecular mass and relative formula mass, and all that. We did it last time. Okay, so find our video and enjoy getting to know the difference. So now that we have our molar mass here, what we do again, when you open our triangle, just cover mass, you'll find out that most times molar mass gives you the mass, okay? Gives you the mass that you're looking for, which is right here in this case. So that will be the solution. This will be our solution. I'm sure you would love me to explain it more in first principles. So in first principles, this is what you would say, and you have to listen up carefully so that you remember. We are finding mass, so the masses will be on your right hand side every time because it's what you're finding, and the moles will be on your left. So you start with the moles. That you can say 1 mole. Okay, remember molar mass is contained in 1 mole of a substance. So 1 mole of sodium carbonate contains these 106 grams, right? Then you'd ask yourself, what about 0.025 moles? And this is when you would cross multiply and have this as a result. Okay, 0.025 times 106, which will give you our answer right there. Okay, that would be it in first principles. Any questions about that? You don't just think of first principles, eh? In other, it's only us, Ugandans, and our UNEP curriculum that use it. In other curricula, like in the Cambridge curriculum, they don't care about first principles. For what? Just have to know how to find these values. That's all. Okay. Those first principles should be just on the back of your mind. But here, UNEP requires them, so you guys are unlucky. But they're also good to know anyway. So the chemist will have to weigh. Again, remember our question was, the chemist needs to make up this and this. How much will they need to weigh? So you can conclude and say the chemist will have to weigh 2.65 grams and dissolve it in water, then make up the solution up to 250 cubic centimeters in a graduated flask. That would be your answer according to the question. That's just including some grammar for you. All right, this is good. I need questions, something you have not understood, please. This is the time we have all the time in the world for you to ask questions if you have not understood. I want you to practice these questions. I'll send you questions to practice over the weekend and all that. I have so many of them. I don't know if you'll even finish them, but I'll give you a few so that I can motivate you to subscribe to Yaaka so that you can access even more. I actually even have some nice videos, some simulations that show the measurements and all that. Okay. All right. Questions? Questions? So is everything clear here? Okay. Let me see, someone has something in the chat. Someone said clear. Okay, Chelsea, say if everything is clear, we can move forward. All right, Faith also says yes, that's good. Awesome, I'm glad. Okay, we can continue. Let me see these other chats. Okay, they're all saying they understood. Okay, Aggie also says clear, Melissa clear. Good job, good job. You can continue and see. So this was our answer and all that. Now let's look at this question now. See what it has in store for us. Okay, Victor also says it's good. Okay, good. We have one here. Another volumetric calculation. It says calculate the concentration of solution of sodium hydroxide. Remember now, it's important as you read the question, you know what we are being asked, because you might make a mistake. So we're asking for concentration of solution, meaning we're finding moles in grams moles per decimeters cubed. And then we have been given that, okay, concentration of solution of sodium hydroxide if 20 cubic centimeters is neutralized by 25 cubic centimeters of hydrochloric acid of concentration 0.1. Okay, that's our question. You can calculate sucks. Yeah, we need to do a lot to change it. But I think it has been changed already. In senior 1, they won't have to suffer with this when they get to senior 3 and senior 5. But so here is our question. What do we do first? What do we do first? We have a question. This is a neutralization reaction. Okay. Sodium hydroxide is reacting with HCl. Let's see. Sharon, tell us, what do we do first?
Okay, here we have to first get the number of moles of hydrochloric acid contained in 25 cubic centimeters.
Okay, good. That's good. Someone has a different idea. Bonita.
We first write the equation of the reaction.
Yes, the equation is key here. In reactions, it is important for you to know the equation. Okay, Charles, you're also correct in the equation. We first write the equation. There are some names here. First, listen. Arthur, Redmi, I think that's a phone type. You should rename your name in Zoom. Victor, Anthony, Lillian, Lutaya, Ivan, Adam. Write your names and contacts in the chat box. Those people I've mentioned. Okay. So it's important to write the equation because we're gonna need the mole ratio. Faith, do you have a question?
Not really. I just wanted to talk about the question. We shall first get the moles of HCl, and then we write the equation between sodium hydroxide and hydrochloric acid. We compare mole ratios, and then it will lead us to the moles of sodium hydroxide.
And then we shall use that to find our molarity, not so?
Yes.
Okay, you have given us a good summary of everything we are going to have to do. Now let's do it step by step so that everyone else can follow. Okay. So that was a good summary. Again, as you've seen, always the first thing in equations, in calculations that involve equations, first write the equation. It will help you a lot, and then balance it. It's important to balance. When you don't balance it, you're going to find a wrong mole ratio, and all your calculations will not be correct. Okay. Okay, after balancing your equation, which is already balanced, then get the molar relationship between the reactants, which is the mole ratio Faith has talked about. So here the mole ratio will be moles of sodium hydroxide are equivalent to the moles of HCl that react. So the mole ratio is 1 to 1, okay? Meaning 1 mole of sodium hydroxide reacts with 1 mole of HCl. Because when we balanced, we saw only silent ones over, okay? So the mole ratio is 1 to 1. You have even 4. I don't know what that means. Someone wrote you have even 4. Okay, let's continue. So now we have the mole ratio. Now, like Faith said, we got the next step of calculating the number of moles of each substance. Okay. So the number of moles of HCl will be 0.1 times 25 over 1,000. In first principles, you see that, remember moles, there is a triangle to that says that moles is equal to molarity times volume, okay? So this is what is here. The 1,000, we introduce it due to the fact that we are changing from decimeters cubed to centimeters cubed, okay? So we have to take care of that. So therefore, in first principles, you would say, or maybe let someone give us that. In first principles, I think I've given you many. You have even annoyed me of the question is hard, it eventually becomes I have no idea what you're of. Question was easy in the chat. Maybe I missed. Yes, Lydian? Lydian. Okay. Please, if you have a question, Lydian, you can always ask, okay? Do not get confused and stay there. All right. Good job. Who is going to tell us this expression? In first principles. It is important for us to know this because, like we said, it's part of our curriculum. If it wasn't part, we'll just tell you that, okay, this is molarity times volume. We have the molarity, the volume we have to convert it into centimeters cubed to account for the decimeters cubed, which is 1,000. We divide with. Yes, James?
1,000 cubic centimeter contain 0.1 mole. What about the 25?
Exactly, so that is correct. Yes, that's correct, James. And Charles has also put it in the chat in words if you want to refer to that, everyone else. Charles, that is also correct. James, well done. So would say 1,000 cubic centimeters contain 0.1 mole. How about 25 cubic centimeters? And then as a result of cross multiplication, you would get this expression at 0.1 times 25 over 1,000. Okay. All right. Okay. Now, here, let me see first this. Sorry, sir, my screen disturbs. Oh, your screen disturbs. Okay, sorry, Lillian, about that. No, you're fine, Lillian. Do not apologize for that. You're okay. So that's the moles of HCl. And now here we can find the molarity. We can say let M be the molarity or concentration of sodium hydroxide. All right. So it will be the molarity, remember, molarity times the volume. Okay, that would be it. In terms of the simple, I'll call them the simple principles, okay? Because the molarity is unknown, but we know the formula of finding the moles of sodium hydroxide will be molarity times its volume, okay? But if not that, what would it be? Let's continue and see, and we'll see what else we can represent this as. So once you've done that, you can just now use our mole ratio here, which is moles of sodium hydroxide are equivalent to the moles of HCl, meaning that this expression here, okay, is equivalent to this expression. You see the trick we have used by using an unknown, okay? We have expressed the moles of HCl as its concentration times the volume. We have also expressed the concentration of sodium hydroxide as its unknown molarity times its volume, okay? But we know that from mole ratio, this should be equivalent to this, okay? Therefore, when you equate the two, you can solve for M, right? This is now mathematics. Now, when you've done that, it becomes way easier. You just calculate and find that M will be equal to 0.1 times 25 over 20. Their 1,000 would cancel out. Okay, their thousands would cancel out from both sides. And then your final answer would be 0.125 molar or moles per decimeters cubed. Now, in first principles, that looks simpler because they leave us limited space in the question papers. Yeah, exactly. They even enable leaves very small space, but they want you to use first principles. But here you can just equate, okay? Here you can use the smallest space possible and you just equate, then solve. You can even solve from right here using a calculator, just right here. After equating, you already know which one is crossing the other side, you already know which one is dividing through, and you get the answer. But we need to know the first principles. So in first principles, we should have first, of course, calculate the moles of HCl. After finding the moles of HCl, they are the same moles of sodium hydroxide. Okay, then we would say the 20 cubic centimeters contained those moles we would find, right? And then we would ask ourselves, what about 1,000? So you get 1,000, okay, multiplied by the moles you would have found here, divided by 25, which will give you this. Okay, that would be using the first principles right there. Any questions on this? Something you have not understood? We used the equating method here, which is just mathematically sound or logical, because you see the mole ratio. Here we are finding the moles of HCl. We got that formula. Then the moles of sodium hydroxide gave us an unknown, which is the molarity we're looking for, and times the volume. Okay, we equated the two. Another person would have just said M times this is equal to the answer you get here. Okay, then cross multiply by 1,000 on the other side, then divide by 20. You get the same answer. It's just mathematics. Remember, mathematics is key here. So you have to do that quickly in your head to know what we're talking about. A question here? Probably something you've not understood. I can always repeat my explanation. Do not feel like you'll be bothering me to repeat what I've said. Nope. Feel free. I actually love repeating what I've said. It ensures that someone else understands it even in a better way. Okay. So any question before we move forward? Let's see. I'm asking if there is any questions. You want me to pardon? Okay. From step 3. All right. Yeah, no problem. No problem. I would love to. Okay. Again, let me go back to 3 so that I can highlight it very well when it is in dark color. So step 3, right here. Step 3 came from step 2. So you have to understand step 2 first. In step 2, we are saying the mole ratio is 1 to 1. So the moles of sodium are equivalent to the moles of HCl that react. Okay? Very, very, very equivalent. 1 to 1. Right? In step 3, all we are doing is finding the moles of HCl and finding the moles of sodium hydroxide. How? The moles of HCl, this is how we find them. Moles of HCl, we have the concentration, the molarity. Molarity times volume. That's the formula. If you go back to the presentation we had last time, the lesson that we had last time, there's a triangle for this. Okay, I made for you a triangle that you can always refer to. Okay, we have explained this also in first principles prior. So the first principles I won't repeat, but you have to know the molarity times the volume. Our volume is in cubic centimeters, right? But our molarity is in decimeters cubed. So we divide by 1,000 to ensure that we have converted to decimeters cubed. It's very, very important. That's where the 1,000 comes from, okay? Because always volume in the laboratory will measure it in cubic centimeters. That's how our apparatus is calibrated. So the 1,000 helps us to convert into decimeters cubed. Okay, so that's it. Molarity times volume. Okay. You can get the answer here. Okay. Whatever answer you get here is fine. You can get it. Then you also have to find the moles of sodium hydroxide. Same thing. Molarity of sodium hydroxide. Remember, this is now what we are looking at from the question. Okay. It's what we are looking at. So, I mean, that is what we're searching for. So molarity, let's make it M, an unknown, times again volume of sodium hydroxide. Remember the volume was given right there. But we have to convert it into decimeters cubed. So we divide by 1,000. We divide the volume by 1,000. So this is it. After here, since the mole ratio is 1 to 1, that means this answer you got here is equivalent to the answer you'll get on this one. Okay, and that's why we equate the two. That's why we equate this to this. Okay, because the mole ratio is 1 to 1. The same number of moles of HCl react to the sodium hydroxide. If the mole ratio was 1 to 2, okay, then we would have to divide this, divide by 2. The one for HCl divide by 2, we'll get the ones for sodium. Or if it was 2 to 1, whatever it would be, you'll just get the fraction and then multiply by what you have. So that is step 3. And then on step 4, we are just now using mathematics. We have equated the two equations. Okay, we are finding M. You can cancel out their thousands and then make M the subject and then find the answer. As quick as that. Okay, Lillian. Sir, you needed to write the state symbols in the equation. Yes, the state symbols are required, but here I was just concentrated more on the balancing and the ratios. But always put state symbols on your equation. Don't get carried away. So I hope this is more clear. Lillian and someone else who said pardon. hope it's more clear. Remember, I'll send out the notes, and you can always inbox me for more consultation or anything. Okay, you're welcome. I've seen your message. All right, and lastly, let's finish up with this quickly. And if time doesn't allow, then we can start from there next week. We have gases next week, so that will be also interesting. So again here, volumetric calculations, care must be taken when dealing with reactions that do not have a 1-to-1 mole ratio. So I gave already an example of this while I was explaining it the second time, that sometimes you can have a different mole ratio. Again, you need to, this, for example, here, sodium hydroxide reacting with sulfuric acid, giving us the sulfate and then water. This means that you need 2 moles of sodium hydroxide, 2 moles of sodium hydroxide to react with only 1 mole of sulfuric acid. That's what it means, okay? So therefore, the moles of sodium hydroxide in this case would be 2 times, okay? 2 times the moles of sulfuric acid, okay? And then the moles of sulfuric acid would be half the moles of sodium hydroxide, which is
sodium hydroxide.
Hey, someone is repeating after me. Exactly, okay? So that would be using the mole ratio that is not 1-to-1. You have to remember that. So remember, it is not a mathematical equation. It's just 2 moles of sodium hydroxide do not equal to 1 mole of HCl. This is not
Excuse
that.
me, teacher.
Yes, please.
The lesson is very good, but the bell for lunch is ringing.
Yeah, I know that. I was concluding. Thank you. Let me conclude here, and then you guys can go for lunch, as the host has said. And the host cares about you so much, so you need to eat. Okay, so again, this is not a mathematical equation. It's just that we are representing the reaction ratio. It doesn't mean that the 2 moles are exactly equal to this, but just saying that the moles of sodium that react will be 2 for each 1 mole of sulfuric acid. That's it. If you have questions, please, you can text them in the WhatsApp group or inbox me. I'll answer them. Well done for today. Let me finish the lesson before the host ends it abruptly. Okay, good job. Well done, everyone. Make sure you ask questions if you don't understand. We shall begin from there next time. Well done. We understand. Good. Thank you. Okay. Thank you for attending. Good job. See you in the next lesson. You're welcome. See you next week. I'll give you some few questions to practice, not many, because I want you to subscribe to Yaaka so that we enjoy. All right, bye.